Hey everyone, and welcome to another explainer. If you're a coating chemist, a formulator, or just navigating the B2B advanced material space right now, you already know that some ingredients just absolutely refuse to cooperate. Well, today we're bringing you a deep dive into one of the most notoriously stubborn challenges in the entire industry. We are going to unpack the microscopic battlefield of carbon black dispersion.
Right off the bat, it's the ultimate million-dollar question, isn't it? Whether you're a seasoned formulator or totally new to the lab bench, you've definitely run into this deeply frustrating headache. You put in the time, you crank up the energy, and yet, the carbon black still clumps, your viscosity completely spikes out of control, and the coating just fails to reach its potential. So why is this specific pigment so incredibly hard to deal with?
Well, to answer that, here's our roadmap for today. We'll start with the dispersion dilemma, look at the extreme physical forces at play, break down the three-tiered structure, expose the wetting illusion, dive into surface chemistry chaos, and finally figure out how to actually win the battle. Let's just jump right in.
So, Section 1, the dispersion dilemma.
Our first stop is really understanding what we're up against here. Make no mistake, this process isn't just basic mixing. It is literally an epic, high-energy clash against the fundamental laws of physics. Pigment dispersion, at its core, is the process of taking dry powder agglomerates, shattering them into microscopic particles, and perfectly suspending them in a liquid resin medium. Sounds straightforward, right? But you absolutely need chemical intervention. Dispersants are your vital tools. They've got three massive jobs. They have to wet the pigment surface, aid the mechanical equipment in physically breaking things down, and crucially, provide a protective shield to keep everything suspended long after the mixing actually stops.
Moving on to Part 2, extreme forces at play.
So, if we add dispersants, why does carbon black still fight back so hard? To get that, we have to look at the extreme physical properties of our formidable opponent. Carbon black primary particles are impossibly small. We're talking usually between 10 and 100 nanometers. Because they're so tiny, they have a massive specific surface area. To put this into perspective, just 1 single gram can have a surface area of over 1,000 square meters. That is absolutely insane. And it's the core of the problem. This massive surface area means extremely high surface free energy. The system is thermodynamically unstable. According to the laws of thermodynamics, these particles have a desperate, spontaneous drive to clump together just to lower their energy. They literally want to aggregate.
And what exactly is the microscopic glue holding them when they clump? London dispersion forces. Now, what's really fascinating here is that an individual London dispersion force is incredibly weak. It's just a fleeting fluctuation in an electron cloud. But here's the catch. A single nanosized carbon black particle contains thousands and thousands of carbon atoms. These forces are cumulative. So when you multiply them across massive contact areas, they are definitely not weak anymore. They add up to become this incredibly powerful glue holding the agglomerates together.
All right, Part 3, the three-tiered structure.
Beating that microscopic glue requires us to understand how this carbon is actually built. It exists in a three-tiered structure. Tier 1 is the primary particles, which are forged at super high temperatures. Tier 2 is the aggregates. This is where primary particles fuse together with inseparable covalent bonds. And Tier 3 is the agglomerates. These are the larger, looser clusters held together by those forces we just talked about. Here is the absolutely crucial takeaway. No matter how much energy you put in with your standard dispersion equipment, you are only ever breaking Tier 3 agglomerates down into Tier 2 aggregates. You will never ever break them back down to the primary particles because standard mechanical shear just cannot break covalent bonds.
Now, the complexity of these aggregates is what the industry calls structure. High-structure carbon black forms these bulky, highly branched chains with massive internal voids. Low-structure carbon black, on the other hand, is way more compact. It has fewer branches. Kind of think of it as looking like a small, tight cluster of grapes. The structure you choose for your formulation radically changes how much liquid the carbon will absorb, which completely dictates the flow and performance of your final product.
Which brings us nicely to Part 4, the wetting illusion.
This right here is a major operational pitfall that formulators face every single day. When you drop a high-structure carbon black into your resin, it acts exactly like a dry sponge. The resin and solvent rapidly rush into all those complex internal voids we just looked at. But it's a total trick. It creates this frustrating phenomenon called false wetting. The liquid fills the voids, sure, but it traps microscopic air pockets inside. This means the actual surface interface of the carbon particle is left completely dry. Your dispersant hasn't even touched the true surface yet. And why does this matter to your bottom line? Because of this harsh reality.
This locks up free liquid, causing a sudden and massive spike in the coating's viscosity. By soaking up all your solvent and resin without actually wetting out, your nice fluid mixture turns into thick sludge. This massive spike in viscosity basically blocks your mechanical shear force. Your expensive lab equipment is in there spinning away, but it's not actually breaking down agglomerates anymore. It just completely ruins your production efficiency.
Let's move to Part 5, Surface Chemistry Chaos.
So, as if overcoming the physical structure wasn't hard enough, chemistry adds a whole new layer of chaos. You might be sitting there thinking, carbon black is just simple, inert, nonpolar graphite. It is absolutely not. The manufacturing and post-treatment processes leave behind this incredibly complex array of oxygen-containing functional groups. We're talking carboxyl, hydroxyl, lactone, and phenyl groups. Because of all this, the surface of your particle doesn't behave like a smooth, predictable sphere. Instead, it's this chaotic, completely unpredictable, uneven mosaic of chemistry.
This creates a huge double-edged sword for formulators. The benefit? These polar functional groups can actually be fantastic. They act as really strong chemical anchors that let your dispersant molecules firmly attach to the pigment. But the danger is pretty severe. These surfaces are often highly acidic and they act like microscopic thieves. They can selectively absorb, trap, and entirely neutralize your other vital formulation additives, like your catalysts, your leveling agents, and your defoamers. Next thing you know, your coating won't cure properly or it loses storage stability, all because the carbon black literally stole your active ingredients.
Okay, finally, Part 6, Winning the Battle.
So let's recap the battlefield. We are fighting a massive surface area, intense cumulative physical forces, unbreakable covalent structures, false wetting, and totally chaotic surface chemistry. How do we actually master this? Winning requires perfect timing. It's a synchronized dance between physics and chemistry. You have to apply intense mechanical shear to physically shatter the agglomerates apart. But breaking them isn't the end of the story, because remember, thermodynamics will force them to instantly clump right back together. So your dispersant molecules have to instantly anchor to those newly exposed surfaces to prevent spontaneous reflocculation. If your chemistry is literally even a second too slow, the physical forces win the battle.
A true high-performance dispersant executes 3 critical steps to create what is essentially a microscopic force field. First, it anchors firmly to that chaotic surface mosaic we just discussed. Second, it deploys steric hindrance. It basically throws out these long solvent chains that act as physical shields to keep other particles away. And third, in polar systems, it establishes electrostatic repulsion. It wraps the particle in an ion double-layer armor so that the particles magnetically repel each other. This exact combination of chemical shields and armor is what guarantees your long-term stability.
And that brings us to the ultimate question for everyone watching today. Is your formulation actually equipped with the right dispersant to win this microscopic battlefield? Overcoming carbon black requires a ton of respect for its unique physical and chemical demands. We really hope this explainer gave you some valuable, actionable technical clarity to take back to your R&D lab. Drop a comment below with your absolute biggest dispersion headache. Be sure to share this with your team and keep innovating. Thanks so much for watching, and we'll see you on the next explainer.